We've seen how a neural network makes a prediction through forward propagation, but the real power lies in how it learns, how to adjust its weights and biases to improve its predictions. This process is driven by backpropagation and optimization algorithms. After the network makes a prediction during forward propagation, we compare it to the actual correct output, the ground truth. The difference between the prediction and the actual value is called the error or loss. A loss function quantifies this error, for example, mean squared error for regression or cross entropy for classification. The goal of learning is to minimize this loss. This is where backpropagation comes in. It's an algorithm that efficiently calculates the gradient of the loss function with respect to every weight and bias in the network. Think of the gradient as the slope or direction that tells us how much to change each weight to reduce the loss. Backpropagation works by propagating the error backwards from the output layer through the hidden layers all the way to the input layer. At each neuron, it determines how much that neuron's weights contributed to the overall error. It leverages the chain rule from calculus to compute these gradients efficiently across all layers. Once we have these gradients, an optimization algorithm uses them to update the weights and biases. The most fundamental is gradient descent. Imagine you're blindfolded on a mountain trying to find the lowest point. You take small steps downhill, constantly checking the slope. Gradient descent does precisely that. It takes small steps in the direction opposite to the gradient downhill, effectively reducing the loss. The size of these steps is determined by the learning rate, which is a crucial hyperparameter. A large learning rate can overshoot the minimum, while a small one can make learning very slow. There are many variations of gradient descent, such as stochastic gradient descent, SGD, which uses small batches of data, and more advanced optimizers like ADAM, which adapt the learning rate for each weight individually, leading to faster and more stable training. This iterative process of forward propagation, making a prediction, calculating loss, backpropagation, calculating gradients, and weight updates using an optimizer is repeated thousands, sometimes millions of times across epochs, until the network's performance converges and the loss is minimized. This is how neural networks learn from data, making them incredibly powerful tools. Up next, we'll see how deep learning connects with other areas of AI.